to spot interstellar visitors like Borisov or the new 3I Atlas object hidden among thousands of comets in our solar system? In this video, I'm going to show you how clustering algorithms uncover hidden groups of comets and how anomalies like interstellar visitors naturally stand out within the analysis. And so I'm going to start with orbital data. And so the orbital data and the values that I pulled came from NASA's JPL small body database, which is an official catalog that astrophysicists, for example, use to track and study comets. So for comets in particular, we'll observe three key features that play a role within my analysis. First, I'm going to look at eccentricity, which is how stretched the orbit is, inclination, how tilted the orbit is compared to the solar system's plane, and perihelion distance. So that's how close the comet is going to get to the sun. And so I fed these into a clustering algorithm called DBSCAN, which enables groupings of comets with similar orbits to appear. And with doing that, we're also able to highlight outliers that don't belong. Now, when I pulled the analysis, most of the comets fell into very stable clusters. So they're groupings that share similar orbital characteristics. But with that being said, as I mentioned, DBSCAN also produces a special cluster, and this analysis is attributed to -1, or the noise cluster. And so the comets that we find falling into that bucket don't fit anywhere nicely, meaning into the other clusters. And often that's where the most interesting of objects can hide. And so for this analysis, I'm going to focus on clusters 0, 1, 2, 4, and -1, that noise cluster, since those clusters contain the majority of comets and objects in the data set percentage-wise. And so one thing I want you to note is cluster 0 is seen in the analysis. That's our standard orbital behavior. Cluster 2, for example, is a cluster that had high inclination rates within that cluster and values. Cluster -1, again, is the anomalies. Now, to understand what really separates these clusters before any analysis is done, we have to scale all the features to some range so that a large number doesn't overwhelm sort of the smaller numbers. And so an example of this is inclination can run from anything from 0 to 180 degrees, while eccentricity could be a value of between 0 and 2. Now in that example, that's not such a large sort of, scale within that range. It's not a huge range, but we still kind of want to minimize that as much as possible, because without scaling, something like an inclination, even in this case, could start to dominate the analysis just because the numbers are bigger values. And so looking at this plot that I have on the screen, this deviation plot, pretty much comparing each cluster to our baseline of 0, which again are our standard orbital behaviors. And so you could see the biggest differences in this come from inclination and the tilt of the orbit. Also, longitude of the node, which is the direction the orbit points in space. And so those two features, for example, can start to assist us in explaining how comet groupings are organized. Now again, eccentricity, the orbital stretch, looks pretty similar for most clusters at this point, so it's not necessarily driving the clustering here, but as we're going to see later, it's the key to finding these interstellar visitors. So if we switch back to the raw orbital values before we had done any scaling, after the analysis was performed, I went back in and matched the data points with the cluster to the original values. Now, almost all comets cluster pretty tightly near eccentricities values that are just below a 1. Now, that's typical. That's what we'd expect for objects that are bound to the sun. But you could see here on this graphic that two stand out. Borisov has an eccentricity of about 3.3. 3I Atlas is even higher. It's over 6. Now, if that eccentricity value is greater than 1, which we're seeing in these objects, that probably means this object isn't trapped by the sun's gravity. And so it's sort of just passing through our solar system from interstellar space. Now you can clearly see on this graphic, Borisov and 3I Atlas are highlighted with yellow stars. Now, my analysis here isn't just bound to comets or even space. We can use the same process to flag anomalies in orbital debris, which is what my PhD analysis was done surrounding. Or we can look at other use cases in anomaly detection. So it can be like fraud, customer behavior analysis. But pulling this back and focusing on space, if we're able to automate a process like this and different anomaly detection methods, we can start to improve space situational awareness. We can spot dangerous objects faster and maybe even catch sort of that next interstellar visitor before it gets away, literally. And so machine learning helps us see the hidden patterns from the universe. Again, we can look at these, comet clusterings, different families, the interstellar visitors, and clustering is helping us separate sort of what we know and the familiar from the extraordinary. Again, those anomalies like Borisov and 3I Atlas. So in closing, if you enjoyed this breakdown, if you're interested in hearing more about some of my research and analysis, hit like, subscribe. Let me know what space AI topics you'd like me to cover next.